Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, sorry for the delay. It's my great pleasure to introduce our speaker for today, Professor James Allen of the University of Rochester. He's a professor of computer science there. He's also the associate director at the Institute for Human and Machine Cognition. And what I really appreciate about his work is that he combines models of communication and collaboration with knowledge representation and reasoning, and he's actually going to give an example of that in this talk. This talk actually won the AAAI Best Paper, and without further ado, here is Professor James Allen.
Thank you. Glad to finally get going. Yes, so what I'm going to talk about today is work we've been doing for the last 4 years on task learning. So the idea is that you kind of want your systems to be able to kind of, in some sense, just watch the user and learn how to do tasks for the user. So can a system learn complex procedures from a single natural demonstration from a user? Where by tasks we mean these procedures you can perform in a web browser, where all our tasks are in a web browser right now because, in fact, we have to instrument whatever the user is using in order so we can track what actions they perform. Natural means it should be like how a person would teach another person how to do something or show another person how to do it. And complex means that we're going to learn procedures that may involve iteration, conditionals, sub-procedures, and other things like that. So these are not kind of just simple straight-line procedures or macros. So our approach is we're going to, as Tim said, kind of bring together a range of different technologies all into one integrated system. First is a collaborative problem-solving agent, which has the ability to do deep natural language understanding. So we're going to extract out a fairly rich semantic content from what the user says. Knowledge representation, some simple reasoning about actions, and heuristic learning with hypothesize and test as we go through and use heuristic methods to identify possible patterns that might predict or reproduce what the user did, and then going off and testing those and keep developing that until we get a solution. And mixed initiative dialogue, which turns out to be critical as we get into learning more complex things like iterations. So here's the outline of what I'm going to do today. I'm going to first give a very high-level overview of the PLOW system, show a video, and show how, so you have an idea of what kind of system we're building. Then I'm going to go into basically what enables this. One large part of that is our language understanding and discourse processing, and then how do we use that and combine it with machine learning and reasoning to enable the robust one-shot learning. We'll talk about an evaluation that was done last year by SRI International on this system, and we'll talk about our current work. So here's the PLOW system. As you can see over on this side up here is actually a standard browser window. When this shot was taken, it was Mozilla. We now actually moved over, and now we're using Firefox. When you see things happening in this screen, it might be either something that the user is typing in themselves or clicking buttons or whatever, but the system can also drive it in exactly the same way. So this will be, as you'll see, this window is going to start changing based on the human computer interaction. Down over here, you'll see the task, a natural language, a pseudo-natural language description of the task as we're learning it. So we go from what we learn to the internal representation of the task, and then we use language generation to come back from that understanding, and we generate out a description of the task for the user to understand. You'll see the speech recognition output when they're using speech over here. There's a dialog window over here, and the user could also type down here. Usually, I guess, in the new system, there's a chat window down below that they can type in as well. And the only other thing on here is this traffic light that gives the user feedback about when the system thinks it's ready for the user to continue, because often when you're learning, there may be uncertain delays in, say, for how long a web page takes to load and other things like that. It's important to keep things synchronized. Okay? So we'll see. This is... oops, hold on. Let's go back and adjust the volume on that a little bit. Can you turn the volume up a little too?
Sure.
Okay, so this is going to be an entire session from teaching to actually showing that it works, and done in real time on on basically a Mac desktop machine.
Let me show you how to find restaurants near an address. Okay, go to this web page.
Oh, what's going on?
Show me. Put restaurants in the place name field. All right. The street address goes here. Okay. The city goes here. All right. The state goes here. Click the search button. All right. Here is the list of restaurants.
Can you check that I understand the information?
Here is the name.
Show me.
This is the distance.
Notice actually what happened there. It goes around a little fast. Is the user actually highlighted one name up there. The system learned how to extract that and then performed it on the rest of the items in the list.
Okay.
Keep the restaurants closer than 1 mile.
All right.
I'm finished with the demonstration.
Okay.
Let's practice.
What is the state address and the city? All right.
You can see over on the upper right, you can see the task executing.
I am finished.
Okay, so that is the system. And as this video is showing, I realize that in the complications of getting all the sounds set up, this is an old version of my talk. So if you allow me 1 second, we'll come back. We'll just use this one if I can't figure out immediately what's happening. But let me just see what just happened. It's going to be too. I don't want to look around. I don't want to know what happened. This is close enough. We'll just go from here. Okay, so that's the system. As you saw, it went through, learned a procedure to go to a web page, extract out a set of restaurants, and then return find the ones that are closer than 1 mile. The one video I meant to show you actually demonstrates that a lot more clearly, so you actually can see it really found the ones less than 1 mile away and things like that. The other thing, we can do complications like the set of restaurants you might be over several pages, and so you might want to iterate over pages as well as over the lists on the page, and we can learn those as well. So what are the major problems? And actually on the revised slides, there's 3 major problems in learning tasks. One is, if you get a kind of a trace of someone performing something, how do you get the correct generalizations? How do you know what the parameters are? What the inputs are, what the outputs are, how various parameters during the steps relate to each other? Or even when something isn't a parameter. Note in that video you just saw, they said, you know, they typed restaurants into that field. That's a constant in this procedure. How do you know that's not a parameter? Identifying the hidden control structures, again, is a how do you, the person doesn't if you go through and execute a task, you don't explicitly show that you've got an iteration here, or this was a conditional, and because of that I did this one over here. However, I would have done something in a different set. Again, a very complicated task. And the other one, which was up here that I put on, was really how do you, once you've got a web page here, web browser here. Every time you go back to this page, it's going to look different depending on both the kind of results you have and the people are constantly tinkering with the pages, and they may have ads on them. The structure changes every time you go back. How do you kind of execute one of these primitive actions, we'd say, on a web page, like filling in a text field? How do you execute that over this wide range of variation that's going to happen when all you saw, in fact, was how to do it on one particular web page? So these are all major problems in learning tasks, and that's why if you look at all the work that's done tasks, it's not very big yet, but if you've done all the work on kind of using traditional machine learning techniques on task learning, they typically require lots of examples before they can generate a model. And even then, the models that can be generated are still fairly limited, say, on dealing with conditionals or other things like that. So the first real insight in the PLOW system, which we suspected was true when we started, and it shocked us in how much it was true even after the first year, is that, well, if you just have people say what they're doing as they do it, the way they describe the task just naturally gives us incredibly rich information for what the generalizations are, because they describe it in terms of the generalizations. And that's probably, if there's any one thing that makes a system work, that's it. And we've seen it to be robust in that, you know, it's not just we made up some things to say that allowed us to do it. If you just put people down and go through and teach things, they just invariably do it this way. It's how they understand the task. So, just to illustrate that, let's look at the problem of identifying parameters. What are the inputs? What are the outputs? How do the various different things relate to each other as they go through the steps? Well, basically, we're doing natural language understanding and discourse processing. So you get the first thing, let me show you how to find hotels near an address. The user's explicitly first telling us that they're going to teach us something. So we know that now we're going to enter into this kind of learning mode rather than, I don't know, finding whether the bus is late, which is maybe you just want to tell it to do something and go off and do it. Or maybe just describe something that it already knows. There's many things a user might do. But they're, again, explicit about what they want to do. So they're going to teach something. We know that this is a finding action. We know from the semantics of find that finding has resultative arguments. And so we know that the hotels, a list of hotels, is going to be an output. That's what we're finding. We know from the fact that we've got an indefinite in here, this is high evidence that this is one of the inputs parameters. So just from this one sentence, we already have kind of a signature for the task model and knowing what some of the outputs and some of the inputs are. Other ones may come in as we go along through the procedure, but I guess it won't happen in this quick example. OK, let's move on and say we move along for a little bit. And the person says, put the zip code here. Well, again, from the deep language understanding, we know that zip codes are part of addresses. It's in our ontology. And so it's basically reference resolution. We're trying to say, OK, this is a definite reference for the zip code. What does that refer to? It should refer to something, most likely something already mentioned. Well, in this case, it's a little more indirect. It's actually referring to some part of something already mentioned. And so we can make that connection. So we know the zip code is the zip code of an address, and reference resolution says, that's the zip code in the input parameter. So that's how we get some kind of dependencies between parameters as we go along. And later on, someone might say, here's the list of hotels. Again, reference resolution. We say, they've identified the output. So basically, the language gives us pretty much robustly the parameterization as we go along. There are other methods, but they all kind of depend on this kind of language ability. By the way, the reason in that video you saw when they typed the word restaurants in there, the reason that the system didn't consider that a parameter was the person described it as they said, put restaurants in this field. And then they typed restaurants. They literally said what they did. And because of that literal match, we essentially say, well, that's a fixed value rather than a parameter. If they'd said, put the business type in this field and typed in restaurants, it would have been a parameter. So one of the first things we have there is, OK, if we can get this deep semantic representation and dialogue processing, we can solve a bunch of the problems. And so there are significant challenges in doing that. We need to produce these detailed semantic representations suitable for reasoning. We have to know things like zip codes are part of addresses. We need semantically aware reference resolution. We need speech act interpretation. And we need, as you'll see in a bit, a collaborative mixed initiative interaction in order to learn things. And you saw that in the video again when they were learning the iteration. The user actually only ever showed one step in each of that in that iteration. And the system, because of the context, could actually fill in all the rest. So the user's actually, you're learning this task with the user not even ever demonstrating one procedure in its entirety. In fact, they only demonstrated a subpart of it. The system filled in actually the bulk of the steps that were executed in that trace. So luckily, we have a lot of that technology, and this is a depiction of the structure of the PLOW system, and everything in yellow is generic language technology. This is what we use in all our different systems. As you can see, we have lexicons, statistical language models. The ones that go over mean that there's a large common base that's domain general, and then additional things are added on in the domain. Particularly in the lexicon, what we're getting a lot is when a web page loads, we want to make sure all the words that are on that web page are in the dictionary. And so we add them all into the lexicon so that then you can recognize them with speech, and we can make at least an attempt to understand them in the language processing. Dialogue management, which includes reference resolution, speech act interpretation, other things like that. Surface generation, coming back from the internal representation to the language. Here's the collaborative agent down here, which again, a large portion is generic, although for any domain, you're going to have to build something very specific for that domain. And then we get this stuff that's just specific to PLOW. We have our task learning execution over here, our knowledge base of tasks, our learning capability to learn on how to produce actions on web pages, the instrumentation of the browser that can actually show us what the user is doing all the time throughout the browser that keeps feeding it into the dialogue manager, so we actually get we get both what they say and what they did, which is synthesized in through this loop. So as you see, actually, the bulk of this system is actually generic. Although, and most of all the work we have done in the last few years, the bulk of it has been on the building these outside parts for this application. Just a few statistics on our language understanding. We have a fairly extensive lexicon. It's rather time-consuming to build lexical entries because we have very detailed semantic information about it. So you can't just add a word. You may have to extend the ontology. You have to add all sorts of different other things in there. We have 14,000 hand-built or verified when they're automatically generated lexical entries in there, all indexed into this ontology. We can actually automatically generate lexical entries at with less semantic detail from resources like WordNet, FrameNet, VerbNet, and name databases. So we can get a word in we don't know, we can look them up, and we'll make a best guess at what it is. And usually it'll be some abstract, we may just know that, this is a organization or something like that, or this is a person or whatever, some very kind of abstract types. But often that's enough to get us somewhere. The other thing I was on the revised slides from this one is actually we can also run as pre-processing things like named entity extractors and other things like that. The kind of whatever statistical models you have, you can pre-run them, and they can all be fed as input to the parser, which helps us with, especially with names and other things like that. Have a broad coverage parser that's really optimized for dialogue, especially spoken dialogue, producing a deep representation, including things like utterance segmentation and robust fragment identification, because a lot of times what a person says is multiple, they say multiple kind of speech acts in one turn. And we have a logical form which provides a flat unscoped representation that can then be scoped. And, I do have it down there. I put it in there. So we support preprocessors. And the final thing we have, which makes this, that allows us to move between domains easily, is because this is all generic up above. But within the ontology, we have an ontology mapping system. And this is what we do for any new domain, is you say, well, I'm going to go from my generic ontology to whatever ontology we need for the application we're in. And so we define a set of rules there. And sometimes you can define some pretty high up in there, so you don't have to define something all the way through. And that will automatically kind of build a representation now given in the structure that you need for your application. There's been a lot, all these are all different systems that we're using this generic capability in. There's a wide range of different domains. As you can see, interactive planning, human-robot collaboration, medical advising, interactive data explanation, and task learning. And they all use exactly the same generic components. So there's no grammar rule in our grammar that's specific to a domain, for instance. OK, so we have that language capability. How do we then apply it into task learning? So now we're going to look at some specific task learning problems and show how the language helps. We already saw how it helps with parameterization. Okay, one of the key things and key challenges in this kind of application is we've got web pages out there, and people select stuff and fill in words and keywords, or do all sorts of different things on web pages. And this is a particular example. How do we generalize that so we can execute it on the next web page that comes up? And I look like I've got to fix a typo up there. So here's a particular example, or quite a simple one, but it gives an example of how we work. So here's a user's going to fill in a text name. This is in looking up, say, let's see, this is a Barnes & Noble. We're looking for some books by Harold Pinter, it looks like. So what happens in this step? Well, the user might say something like, put the name here, or put the author's name here, or put the author here, or put the author in this text field, or all sorts of different things I can say. But generally, what we're going to get is we're going to be able to parse this down, and through the generic into the ontology mapping, we'll end up with saying, OK, this is some sort of filling action with where the object being filled in is some semantic type of a name type, name of something. And the user types Harold Pinter into the text field. So what do we get there? Well, we observe some sort of action at our semantic level of instrumentation. This is filling a field. The field that's filled in is some DOM node called, input 22, say. and the input, the value that they put in there was Harold Pinter. So this is the input to our learning. Now we have to learn how to redo this again. Well, what we do, actually let's go back for a sec. What we do is, okay, well we know, we can look at the DOM tree here. So we see input 22 is right there. What we start doing is we start searching around through the DOM tree and say, okay, we know semantically what we're doing is we're putting a name in some sort of field. Okay, so we have a semantic characterization. We start looking around and saying, what is there about this subtree part of the DOM that could allow us to find that again? And so in this case, say, this is a pretty typical structure you find at least on Barnes & Noble and things. You go from this text field over here, you go up a little bit, and then you come back down. There's a sibling over here, and this has a node, and it's got a tag in there that says author's name. Very conveniently. The fact is that if you look at DOM things, there's tags all over the place. People essentially kind of comment and do comments through their pages. We can actually parse this. In this case, it's pretty simple. We're looking for a name, and we've got a name there, and we say, that's great. Okay, so we're going to learn a pattern here, hypothesize that this is we're looking for a subsection of the tree where we're looking for a text field that has a sibling over here which is labeled with some name, labeled with author's name.
So this part may be a bit ambiguous, right? Because there may be some other reviewers name.
We'll immediately run this on the DOM tree and make sure it's a good pattern. If it doesn't get back the same thing again, then they'll keep looking for another pattern. But at least we'll find one that works for this page. Okay? The other thing we're doing is we're doing language understanding as we go along here. So this was an easy example because we had name and we're looking for a name. But the example I often use is someone might say press the search button. You look through here and there might be a label, a tag on it somewhere that says find, or something like that. And we can actually, through the semantics, know that search and find are very closely related actions. And so we'll say, that looks like a match. So we're doing a semantic matching here rather than just a text matching. So we'll learn something like this. To find a text field associated with some type at this site, Barnes & Noble, we find a text node that has a sibling node of type text whose content is a linguistic realization of the type, or something like that. Kind of captures the generalities I've just talked about. Okay, so that allows us to find the node. So then we're going to learn the step. The step we see in the procedure is, well, here's the action, which was fill in the file, fill in the field where we had the name, some text to fill in. We find the node in the DOM tree, and then we perform the fill action. Through our instrumentation, we can perform any action. We can basically have actions we can observe. We can also execute back. So we can actually perform the action in there. And then we're done with the step. And this proves remarkably robust. Luckily, people tend to build pages that help us with this. If we can't find anything like this, then we'll back off to less desirable methods, like looking at kind of structural aspects of the page. Like maybe this is, I don't know, the 8th text field on the page, or something like that. And we'll learn that pattern. Generally, those are very fragile, and they'll soon break and won't not work as the pages change. Yeah?
To what extent is this truly makes initiation such that, for instance, let's suppose there were an ambiguity with the author name or something, where the system maybe demonstrates what it thinks it might be to the user, and the user says, no, that's not it, this is it.
Yeah. You'll see there's a little bit of that later, not in this case here, because in fact, if we find a pattern here, we know it works for this page.
Okay.
That's our strategy. So,
but does it have as part of the architecture, does it have some reasoning about giving feedback and grounding and so forth for confirmation of status?
Yeah. You'll see that especially in the iteration, where actually it's a fairly clear-cut case of what we can do, because actually we are executing that on a series of different contexts already, and so there's a chance of that coming up. The way we've designed this right now, there's not really an opportunity to do that here. The other thing is the user can't see the DOM tree, so it doesn't make much sense to start talking about it. OK, so here's learning iterations, which you saw in the video. And I think I've got a I hope in this version I've got to show it another one. But this is what you saw there. They had a page, and they said something like, here's a list of hotels. And they highlighted that section there with our little DOM selecting tool that allows us to go through and essentially pull everything in under a DOM node. And it highlights that list there. The system actually recognizes from the description that this is a list of things. And so it'll take some initiative and say, OK, well, if there's a list of things, I have to try and figure out what the list is, what the elements are. And so I'll go through, and this one, it uses structure mapping. It tries to find parallel structures all the way through. And it'll come up with a list that you saw in the video like this, a page here, which will generate out a set of entries. And then it'll say, check that I've understood this correctly, or something like that. And then the user can go on from there. Now, the user might say, OK, well, now I need to extract various things out of this. I think in this one, they would extract out the name and the distance. So the user might highlight this part here and say, this is the hotel name. OK, what the system will do is actually each one of these is essentially now looks like an independent individual web page. So it'll use the same learning techniques it has to try and find this, extract this text out of here. If it's a node within it, it'll actually try and use the patterns on the node things. If this is all mainly text, it'll have to learn some regular expression on the text to try and get it. As soon as it gets one, the system will then execute that on all the rest of the records it has, and then present it to the user. If the user doesn't like it, they can say that's not right, and they can give them another example. And I don't know whether the video, because I don't know what's here, whether the video shows that or not on coming up. But basically, so by the system taking initiative and doing things, presenting stuff to the user, asking for them to look at it and approve it, and do corrections, they'll go through and get that. And so that's all driven by this model. This is our kind of another view of the system, more kind of functionally focusing on this collaborative agent. So we have the whole kind of language system and understanding and interpretation of actions up here. So this is really an intent recognition process that eventually comes down where we get observed actions of what the users have said and done. There's a collaborative agent here that's constantly running, and at each stage it's then deciding what the system should do in order. It actually works back and forth with the identification of intent to make sure you get a good interpretation. Then it decides what the system has to do in order to progress further. If we would say, if a person had said something like, I don't know, find me restaurants within 1 mile or something like that, they just started up there, then the system would interpret that as a request to perform an action. It would then look up in the knowledge base here to see if it can find an action like that. And if it can, it would then go off and it would go to start executing it. And it would ask for just like in practice, it would ask for the information it needs. If you're in the middle of learning, then what will happen is it'll come down and someone says something like go to Amazon.com. It'll come down through the agent and says, OK, I'm in the middle of learning. What I need to do is invoke task learning, learn the next step. And what we saw in iteration learning is you get a combination of all this. So we know we're in the middle of learning an iteration. We come down, we learn a step, we go through and we learn that step. And then because we know we're in that context, what the system's going to do is then take what we just learned and then execute it on all the others. And so we're actually executing those steps as we're learning it. Can also do it another way, not necessarily in iteration, is if a person's teaching a procedure and they describe a step that we already know how to perform, the system can come back and say, I know how to do that. Would you like me to do that for you? And then they'll go off and do that part of the task for you, so then you can go just teach the rest of it. OK, now I think then we're going to see a little bit of this. Again, I don't know which one this is. This is similar to the same one, but you'll see this. Just see it happen again.
Can you check that I understand the information?
Well, not what I intended to happen. Okay, well, let's just look at that example. That was supposed to go on, but that's not worth it. Let's just look at just the internal, the collaborative problem-solving state. This is what drives the core of the system. It's basically a collaborative problem-solving model, and when we're learning, of course, it's all about learning. And so I have over here just kind of the goals that the system has at any particular time in this dialogue. So right now, it's always doing something. It's down the bottom, and we know we're in the middle of learning a task. And at this stage, the person says, I guess the next slide. Here we go. Okay. So now the person says, here's a list of restaurants. We do the understanding on that. We recognize, okay, they are identifying a list of things. With our intention recognition, we go back and say, okay, we're going to learn iteration. Okay? So we're going to do that. We go through, we try and our part of doing that collaborative task is, well, we'll first try to parse that list. So we go off and tell the system, try and parse this. If it succeeds, it'll come back. It'll then present it to the user and then ask for confirmation. So it throws up the screen, and here it is. And basically, basically says, is this OK? So it's an explicit confirm. The user could say no or whatever, and then we might try it. Although it's a system that's a little weak in trying to recover from this kind of error, or the parsing errors right now. But what we want to do is go back, and then we could give us another example of an element in the list. And that will give us more evidence for how to parse it. But the user may also just, even though the system did that, the users often just ignore what they're there. So it's going to be implicitly confirmed because the user just goes on. So the user just says, here's the name. Okay, so we get rid of the confirm. We know from this context that, okay, we're learning an iterative step. And we have an example. We're going to go through and do our learning and try and learn that action on this little page up here. So we can do it. And then we're going to then go through, and the system's going to take some initiative and then apply it to all the fields. And go, down it goes. And we're going to build a column, which is that column you saw over there. And we're going to then wait for a confirmation. And again, the user might say, this is wrong, and then the system will come back and say, well, give me another example, and you could go down to one of these where it didn't work and highlight that, and then it would do the whole thing. Or a user might just go on, and now or they might say OK, and we know it's OK, or they might just go on, and we'll implicitly confirm it and move on. So that's basically what's driving this kind of interaction as we go along. So there's this kind of collaborative problem-solving model that we built that shows how to be involved in this learning process. And we have similar kind of models on how to work with a user to execute a task, which are generally much simpler than this. Or what we would have is ones to describe tasks and do other things like that. There's one for practicing and things like that.
It seems like with respect to the goals that you have there,
yeah.
that it can be abstracted to be generic, right?
Oh, sorry, yeah, that's a good point. These are all generic. This is all on the generic side of the system. Yeah, right. So this is all about task learning.
But not the column, the confirmed column. I guess it's an instantiation, I guess.
Right. That is actually how. Now that's part of the generic capability on task learning, because the system's generating this GUI here, and so as you'll see, we're doing task learning now in different environments. We'll use the exact same technology there as well. This is sort of our intuitive learn iterations panel. Okay, let's move on. Okay, so how well does this work? Well, this has all been mainly developed within the DARPA PLOW program, and because of that, in any DARPA programs these days, as people know, there's a huge emphasis on evaluation, which actually turned out to be good for us, because actually SRI did a very expensive evaluation, which we probably could have never afforded to do of its system. So we gave them the system. And this was the task learning part. The PLOW project's monster thing. So this is just a small part of their evaluation. But this is what happened there. There were actually 4 task learning systems that were developed under the PLOW project. We have PLOW up here, which is, as you just saw, combining language and demonstration. We have another system which is essentially just taking observations and just trying to learn from the series of observations, no language. We have another system that is essentially like a GUI, where you kind of try and describe a task using a GUI. And the last one is basically a task editing system. So you have an existing task model, and you can go through and essentially do add steps or other things like that, mainly through a GUI and some natural language retrieval. So we have 4 systems coming in, 16 subjects. There was extensive training and multiple practice examples, because the first thing you've got to do in these programs is, of course, pass the go, no-go test. So there was a set of questions for the go, no-go test. And all the training and other stuff like that was focused on that, and they did that, and they passed the test. But we already knew there was a list of like 200 questions that could have been asked in the test, and like 50 were asked or something like that. So we already had some idea what questions were going to get asked. And we did quite well on that. In fact, the system passed, and we got very good scores. We pulled up the score a lot, and it just passed over, the boundary. So we got our funding for the next year. But this is the interesting thing then was the new task evaluation. In this one, the evaluators actually made up 10 new tasks, which we'd never seen before. Okay, and they developed a scoring scheme for each and all those other things. And then all the 16 subjects came in, and they had a day to try and solve these tasks. And depending on the subjects, some of them actually worked pretty hard at it and worked all day. Some of them only worked a few hours and checked their email and did other things. But so it's but anyway, it's hard to ask people to do something for 8 hours straight. And produced from that were a set of learned task models that then came in. The evaluators again then had 3 test inputs per task that they used to evaluate and see whether the task models worked. And there's a grading scheme, so you could get partial credit depending on how much of a problem you solved. So say you got to the right web page, but you failed to get the information off the web page. Well, you'll get a certain score for that, but not perfect, and various things like that.
So with respect to the other system,
Yeah.
did PLOW use speech or no?
They used chat window on this one. Right. We actually played around with using speech, and then we decided we want to take that variable out.
So in your evaluation, are you going to evaluate also the learning curve of the 4 different systems?
No, this is, you'll see what we have in the evaluation, and at the level of sophistication of these systems right now, this is about as much as you can get. The learning curves we're not quite ready for learning curves yet. Yes?
So did you notice a difference? You said you were relying on the generalization from the user's input in speech. You notice a difference when you went to text chat in how rich that input was, or was it just as good?
No, it was just as good. Cool. Okay, so the interesting measures are, of course, well, how well could they teach tasks? How many did they teach, and how well did they work? But also with this kind of evaluation, which systems did the user prefer? Which ones did they find usable in order to define things? Just to give you an idea of questions that were asked, these are the 7 questions out of the 10 that PLOW, at least one person was able to teach a procedure for with PLOW. The green ones are labeled because they're the easy ones. They're ones that are fairly similar to things that we'd seen before in the exam. So they're variants of things in the exam. These other ones in orange, and I guess we have Actually, still, because we haven't looked, we have no idea how they solved these things, or what web pages they went to, what they used, or in order to solve these problems at all. Yeah. 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 Well, they could teach as many, tried to teach as many of these things as they could. There's 10 tasks, right? There's 10 of these, yeah. Well, you'd be surprised. I mean, there's, yeah, right. I mean, that's one of the problems right now. I mean, although what the results I'm going to show are promising, right? This is, it was difficult for the users. In fact, most of the systems turned out to be ours, you know, kind of, as you'll see, ours kind of did quite fairly well on usability and on how well the task models were built. The other systems didn't do so well, and at least one of the systems was very hard to use. Yes, they had already gone extensive practice and done the exam on this, you know, where there were these. It's the same 16 users. So these are users who have had, we gave them about a day kind of tutorial, and then they had a bunch of time to practice, and then they did the exam. People actually, there was a lot of excitement about our system, actually. They found it difficult to use. We've done the evaluation this year. They liked it a lot better. We got rid of a lot of the technical reasons. I mean, one of the things that was difficult in this one was, you know, these systems are so fragile as users make up mistakes all the time. They say the wrong thing, and yeah, we can support some backup, but you know, if you're in the middle of an iteration and you do the wrong thing, the chances that you're going to be able to recover are almost nil. And so most users will, at that stage, just give up and start from scratch again to define the procedure. And we've worked very hard to do better than that, but that's the kind of thing that would happen. Or the other thing is, you know, they go off and they find web pages, and depending on the web page, you know, they go to a web page and it's all looks great, but it's all flash code or something like that. We can't find anything that's going on, so we can't learn the extraction patterns. That's another thing. So they have to kind of, to learn a task, you have to do some experimentation and find out what websites might be promising, do that, and then figure out how you might go through. The other thing is, you know, that then, you know, the language they were using here, maybe they, you know, they start saying things that the system, we didn't know they were going to talk about, you know, some of these things or whatever like that. So they might phrase things in a way the system just couldn't understand.
So do you guys have a recording of everything that
Yeah, we have all these sessions, yeah.
It'd be really interesting to start sort of like teasing. I don't know if we just spent the time teasing the part of where are really the major problems.
Yeah, well, there were so many problems on this one that actually this year's evaluation would be no, I guess that's no. The problem is that this year they didn't redo this evaluation, the new task evaluation. They only did the exam, and so which was unfortunate. We really wanted them to do this test again because I think we would have shown some significant improvement. But anyway, here's the results that came out of that. We had, as you can see, there were 55 task models built successfully over the day. 30 of them were built with PLOW. So we got the bulk of the, you know, the majority of the tasks were used our system. That says a lot about usability, at least compared to the others. Also, PLOW was used successfully by the most number of subjects, 12 out of 16. Some subjects didn't solve any task at all, so there's a couple that are kind of out of the running there for whatever reason. And in addition, PLOW, besides solving the most number of task models, actually received the highest grade on the resulting performance, which was 2.2 out of 4. So it's kind of a whatever, B or whatever. So it's, you know, it's not stellar performance, but was pretty encouraging. We were scared. We were terrified of this exam. We couldn't believe that we were going to really deliver this system and it was going to be out of our control, and then they were going to sick all these users on for tasks we'd never seen before. So it was a huge sigh of relief when these results came back. So that's how it works on the others. We actually got higher scores on the exam test, and actually going from, we got about, I think, a 2.85 score on the exam. And this year we got a 3.25 score on the exam. Yeah?
So that question about the number of subjects you say on system 1 versus yours.
Yes.
On the right, the bars are kind of similar from where I'm sitting. But on the left, the bars are totally different. Is it users get to vote with their feet as to which system?
Yes, that's right. That's what they did, yeah. So what was, what's the, this one, well, this one's the average, whoops, sorry. This one's the average grade. This one is this is the number of users that successfully used the system for at least one task. So the users voted with their feet on this. They went into the room and they had all 4 systems sitting there on their desktop, and they could teach, tasks by using whatever one they wanted.
Can you say the types of the other?
There was one that was just doing no language, just learning from scripts. There was a GUI editing tool for editing existing procedures, which actually, that's this one here. It wasn't really appropriate so much for this kind of build new tasks from scratch, so it didn't do very well. And the other one was this, was kind of a GUI kind of task construction toolkit that went through, and you could kind of define steps and give it an insight into how to find or retrieve information from web pages and other things like that.
So very few subjects actually use all 4 systems, right? Almost none.
Right, right.
Some of those bars don't
Yeah.
anywhere near 16 times 4.
Right, exactly.
It's like sort of 12 use your system and 4 use the other system.
Right. Right. As far as right. That's right. Right. I mean, well, we got one question maybe, but these were the 2 that which I think are the most usable, which was ours, which is the just demonstrate the task with language, and the other one is Lapdog, which is just demonstrate the task. So they're the easiest ones for the user to use because they just have to do the task, and the system does the learning. Turned out the ones with the GUIs for trying to get the user to be were more like a little bit like a programming, and so the users generally found it too complex. These were fairly technical subjects. These were mainly SRI employees.
In what field? They're not programmers?
They may be a range of different things. Some were programmers, some not.
So what was the difference between your system and the one that then from the integration without number? What did the user identify as the advantage of this?
Well, it learned tasks faster and better, basically.
Like it's not, I mean, it would be interesting to have an evaluation where you sort of strip the language out of PLOW. Like,
Yeah. Well, this is close to that, right? This is essentially that.
Is it like, for instance, like PLOW supports, right, these iterative things through lists?
Yeah, right. Nobody else could do anything that complex, right?
Right. So, but there might be a way of doing that without language necessarily.
Maybe. I'd like to see it.
Clear. Yeah. Right. So.
But you see, this is, and it's not exact, right? So, but they really worked at this, and they really tried to squeeze everything they could out of the observations, and I think they did a good job. But things like iteration are just way beyond. And you see, it was quite usable. 8 people got a model, and it actually, but it didn't do so well in the scores. It got about a 1.5 versus 2.25 or something like that. Yeah. The grade, this is the average grade over the task that the system solved. So this is a right, exactly. So this is a score of 2.2 out of the with the 12 users on 55% of the tasks, and this is like 1.5 out of whatever this one is. System 2 is 24% of the tasks. Yeah, I think we didn't do an analysis like that, but I think I think there was some effect on that. And some of the ones, different systems targeted different questions on the exam. And so if you had a question that was similar to one on the exam that was, and that system had been, targeted to that, then it generally will do better on that question than the others. Yes, this is just the total number of tasks that were defined by each of the 16 users. So, that's right. Yeah, well, and they could have, although I don't think anybody did, they could have solved the same task in 2 systems, and it would have counted twice in this evaluation. Actually, I'd not thought about that, but that would have done. But nobody did that. But it would have happened. But you're right. That's if we ever redo this, that would be a constraint on to make this a little more respectable. So yeah, so still, as a formal evaluation, it still has some holes. But believe me, as far as when you get into dialogue systems, and actually, that are doing very complex tasks, this is as extensive evaluation as we've ever seen. We were delighted that it happened. Of course, once we saw the results, we were delighted that it happened. Just to see, these are 3 questions that PLOW couldn't learn. So it got 7 out of 10 the users could do. Again, we don't, looking at these, I can't particularly tell why these were more difficult than the others, although they're all actually, this one we would not have been, we can't do, at this stage, Year 4 system could do our simple arithmetic, like comparisons. This Year 3 system couldn't, so we would have just had to, if we got that far, we would have had to randomly pick a travel expense. But even if someone had done that, we would have got at least 1 task model. It wouldn't have got a good grade. So they didn't even get a bad solution. We didn't even get a bad solution from the users for these 3. Okay. I believe that's true. Yeah, right. I think some of these, yeah, some of these project things are clearly SRI's using some internal website to do, which we'd never seen. Oh, this one actually, I know why this one we didn't do. It's the GSA websites were monster difficult to try and navigate through to try and get to things. So there's a lot of, we actually have this one. This question now works on a year, but it took us almost a year of on and off solving problems in order to knock down all the technical difficulties, mainly on interpreting the web pages to go through this thing. There are things like, so you've got to select the right state of a map, and you've got to go through, and now you've got columns you've got to go through, and you've got to find but sometimes, the per diems are rated by the city, sometimes they're by the county, and then you've got various different issues like that, and then sometimes they're not listed at all, and there's something up the top of the page that says, well, if it's not listed here, the per diem's this. So they're immensely complex. But we do have versions of that now. We still haven't got the default for the state, though. Yeah.
So to some extent, it seems like doing well on this kind of task depends on how well the underlying architecture interprets websites and
Yeah.
fields in the website and so forth. Have you looked at the other systems to see if, like, if you look at all of the systems, right? Could these differences have been sort of accounted for by, lack of good DOM parsing, for instance?
No, I think
Roughly the same.
I think that's mostly roughly the same. I think it's true. I'm pretty sure we had the most sophisticated DOM interpretation of these projects. So it is, yeah. So we haven't factored that out. But generally, it's the usability that was the killer, right? Because I mean, even if you could define a bad model for some of these, you would have at least got 1 out of 4 or something like that. Even if you just get to the initial web page and maybe click on a link appropriately, you probably get 1 point or something. So a lot of it, I think, these are usability issues as well. So yeah, right. So I've already kind of talked about this. Well, it showed that people could sexually. It doesn't mean it was easy to do it. It was pretty miserable results, but it's the first time we tried it. On average, each subject only taught 3 tasks total over a single workday, although it varied a lot between subjects. Some had none, as I said. I think someone 6, I think. And a bunch of problems can be solved with better engineering. We did that this year, and anecdotally in the exam, they said it was much improved. But we had a bunch of tough issues. These are things that we really need to do better and we've been working on. First, once you learn a task, can we debug it from execution failures and other things like that, or adapting procedures to new things. Instrumentation remains a critical problem. But let me just show you quickly what we're doing. There's another application we're doing right now is we're actually working within, this is a telnet window. This is how the military makes their bookings still. The entire military system. And, you know, to make a simple booking, it's, you know, type in the thing and then click on escape F11 or whatever like that, and off you go to another page. And they're still using this system because the new one that was built is even worse. So they're still using this as their old system. So it's very painful. And they've tried to develop macros and other stuff like that, which helps a little bit, but generally it's too complex for that. So we're building a version of the system now, which we're going to, I think, call plot rather than plow for telnet, where we're actually going to, the instrumentation now, we're actually going to do some sort of parsing on this whole page so we can get a structure out. So we'll be building our own kind of equivalent of DOM here. So we expect this to be a much friendlier environment for us to do task learning on the instrumentation side. On the other hand, the procedures are way more complicated. There's lots of conditionals and all sorts of other stuff depending on what goes on. But let me, so we got to redo the browser. Actually, for the most part, the system moves right over with just minimal extensions. And as I said, the major technical challenges. I just want to move ahead quickly because I want to show you one more video. Here we are.
Your plane landed 2 hours late due to thunderstorms. You need a hotel for the night. You pull out your iPhone and email your PLOW personal assistant.
Hi, I'd like to make a reservation tonight at government rates.
The PLOW personal assistant that answered the email is an automated system that can understand and generate email messages using the TRIPS Deep Natural Language Dialogue system. It can perform tasks that you have taught it previously through a web-based interface. In addition, you can import tasks that other users have defined and wish to share. Consider a simple example of defining a new task. You want to define a task to find restaurants near companies that you visit. This is done easily as you can reuse tasks previously defined. We assume that you have 2 tasks already defined. One to find the address of a company, and the other to find restaurants near an address. In this session, you define a new task that combines these capabilities. PLOW connects the input and output parameters appropriately so that the combination works. This is the login screen for the PLOW server. You start a new session. Now you inspect your local tasks. You already have a task to find restaurants near an address, so now you only need a task to find the address for a business. Looking at the public tasks, you find one and import it. Now you can define the new task. Using the chat window, you introduce the goal to define the new task. Now you define the first step, to look up the address for the business. PLOW recognizes it, knows that task, and inserts it for you. You now define the second step. Again, PLOW recognizes it, knows the task, and inserts it. The task definition is now done. You can browse over the task definition to make sure everything is okay. The task is now ready for execution. You could test it through the web system, but we'll show testing it using its email interface. You send an email to PLOW requesting that it perform the task. A minute or so later, the reply is received. There are many ways in which you could have invoked this task, some involving multiple exchanges of email in a dialogue. Here are a few examples. Also note that to effectively combine the procedures, PLOW needs to be able to understand parameter values such as addresses. The address returned by the first subtask needs to be interpreted so that the appropriate fields can be filled in the second task. WebPlow provides a convenient way to provide access to the system from any platform that supports the Firefox browser. The email interface provides a valuable way to access your tasks while on the road.
That's our latest. Okay, well, thank you.
Okay. Yes, we have time for questions, although people have been asking a lot of questions throughout. Okay, well, let's thank our speaker again.
Thank you. Sorry we started so late.